a few other people. All right, there we go. So thanks everyone for calling in. Our speaker today is Chad Spooner. Chad is a senior scientist and engineer at Northwest Research Associates in Monterey. He got his PhD in electrical engineering from UC Davis, and he's also an adjunct professor at Virginia Tech. So Chad is an expert in cyclostationary signal processing techniques, and there's a couple applications for this in radio astronomy. One that we're not going to talk about today is in the realm of pulsars, which is something that I and others are interested in. The other is for RFI, radio frequency interference identification and classification. And that's how I kind of got into this and actually made contact with Chad directly. So Chad also maintains a really excellent website called cyclostationary.blog. I highly recommend it for anyone who's interested in any of these techniques. And so it was a great resource for me as I was first and still am starting to get into this field a little bit. And I had posted a question in one of the comment sections, and Chad was kind enough to reach out via email, and we've exchanged a few emails since then. And he's even analyzed some of the data that we've been taking for this project. And so we were hoping to get him out on site in Green Bank to give a talk back in April. Obviously that didn't happen, but we're very happy that he was able to join us today for this lunch talk. So he is going to tell us more about cyclostationary signal processing techniques for signal detection and characterization. And I will turn it over to him now.
Okay, so thank you very much, Ryan. And I also want to thank Natalie Butterfield.
Session.
Sorry, what's that?
No, I think just make sure everyone mutes themselves if they're not speaking.
Okay. Thank you, Natalie, for your organization and all the scheduling. Appreciate it. I'm going to get right to it because time is short since it's a lunchtime kind of talk. I want to repeat that I'm not an astronomer or a physicist. So I'm an electrical engineer. I work at Northwest Research Associates. We call ourselves scientists because most of the people that work here are scientists. And then there's some engineers like me, but so keep that in mind. I specialize in CSP, cyclostationary signal processing, and mostly I apply that to the problem of blind signal detection and characterization. Blind meaning I don't have any prior information about the signal that I'm trying to detect and characterize. Now I think with my conversations with Ryan that we have a mutual problem. I want to detect and classify all man-made radio frequency signals for a variety of reasons, but you guys want to detect some man-made RF signals because they're causing you problems. They're obscuring your view of astronomical signals. So hopefully we can work together, or you can take something from these techniques and apply them to your work, and it'll help you do the science. So that's what I'm trying to do here, is just help you guys do science. And then, as Ryan said, go to the blog. It's listed at the bottom here, just cyclostationary.blog, and there's a lot of information there about how all these techniques and all the background and all the math. The talk will be a little light on math, of course, because we only have a few minutes. So here's where I'm going to go with this presentation. First, an introduction to CSP with some little bit of math and some mathematical concepts that are illustrated with cartoons and things. Then we'll talk about the problem of interest, this modulation recognition problem, which goes by a bunch of different names: signal classification, automatic signal classification, signal recognition, RFI characterization, etc. They're all pretty much the same problem. Then my solution to that, I'll sketch that, which is I call it the multiple signal scene analyzer. And the Whisper system is an embodiment of the MSSA that has hardware and acquisition capabilities. Just sketch that, because then I'm going to apply that, or I have applied that, to some GBO supplied data that Ryan gave me. And then we'll look and see what we can discover about some of the signals in the data and how we can characterize them. And one of the reasons I think you might want to characterize signals like this is to point a finger. So we're not trying to demodulate the signal. That would be very difficult if we had to demodulate every single signal that we could possibly find in these bands in order to point the finger at who's transmitting that. signal. We're looking at the external information in order to point that finger. But then at the end, I do want to sketch a little related area called fresh filtering, which is a kind of signal separation algorithm. So can we, in the case where we have a radio frequency modulated interferer masking our astronomical signal, can we remove that co-channel signal without substantially disturbing the underlying natural signal? So I'll just sketch the fresh filtering. Okay, so CSP. So if there's a one slide CSP concept, this is it. So in the time domain, cyclostationarity just means the ability to generate sine waves using nonlinear transformations. So think of a squarer or raising the signal to the fourth power. We pass it through that. We look at the output. If we have sine waves, non-trivial sine waves, that is, sine waves without whose frequencies aren't equal to 0, then we have a cyclostationary signal. In the frequency domain, on the lower part of this cartoon, the CS property means if you look at distinct subbands of a signal or some data, that they contain correlated information. The information is somehow redundant between those two bands. So in the case of the time domain, when we're squaring or raising to the fourth our signal, we get out sine waves with certain frequencies. We name them alpha and we call them cycle frequencies. When we look at the separations in the lower plot between correlated bands, those separations are the same numbers as the sine wave frequencies in the upper part. So it's really just two sides of a coin, or two ways of looking at the same property of a stochastic process called cyclostationarity. The key to all of it is this set of numbers, the cycle frequencies. So we'll be talking about cycle frequencies a lot. That's the primary way we're going to discuss or describe the structure of the signals in the GBO data. Unfortunately, we have to carry around two of these spectral correlation functions because we want to deal with complex valued data. So we're always going to be talking about a non-conjugate spectral correlation function and a conjugate one. And they reflect different parameters of a signal. So sometimes the conjugate one's really important, and sometimes the non-conjugate one is important. And we'll see that through a lot of the examples that I show from your captured data. And so, fine, we can talk about the correlation between these pairs of narrowband components, but how do we really visualize that? Well, we can graph that correlation value as a surface over an F alpha plane, F being normal spectral frequency, alpha being our cycle frequencies. And so on the right here, I'm showing such a graph of a spectral correlation function for a very common modulated signal called BPSK, just a binary phase shift keyed signal. And you can see, the functions as functions of F are continuous, right? The parameter varies smoothly across F. But for cycle frequency, it's a discrete parameter. There's only a few cycle frequencies for any signal. A lot of different spectral frequencies can have energy, but only a few cycle frequencies. And so that's how we're going to visualize it, both for the GBO data and some examples leading up to the GBO data, using these two surfaces that we carry around, the conjugate and the non-conjugate spectral correlation function. And I focus on the frequency domain characterization so much, and as do others, because when we estimate these things, it's the way to go. We can leverage the power of the FFT. So we tend to work in the frequency domain with cyclostationarity, even though all of this stuff there's an equivalent formulation in the time domain. Okay, so let's ask and answer a few questions to orient ourselves on CSP. Why do we care? Well, why is this useful? It's useful because of signal selectivity, which is a kind of tolerance to noise and interference. So here's an example of those two surfaces I talked about, the non-conjugate and the conjugate spectral correlation functions. For a synthetic scene I created that mixes up direct sequence spread spectrum signal and a BPSK and some other signals. The little dotted lines on the upper part show you the power spectra of those constituent signals. And so it gives you an idea of where the noise floor is, and gives you an idea that if you looked at a spectrum analyzer at this data, you would see that black line at alpha equals 0 in the upper plot, but you wouldn't really know how many signals are present or what their types were or anything like that. So they're mixed up in the spectrum. But if we look at the rest of the surface, all the different cycle frequencies in both of the planes, the features for those different signals appear in different places in F and alpha. And so they become, in a way, unmixed. And we can start to identify each signal type, and we can also obtain high resolution estimates of parameters of interest, like symbol rates, chip rates, carrier frequency offset, things like that. Okay, so that's the real power of this, is when you have multiple signals, co-channel or not, whatever, just multiple signals in noise, you can do estimation tasks that you can't do with stationary signal processing or the spectrum. And then the next slide is just, yeah, that's fine, but what about real data, right? So here's a surface for a scene with nothing but captured waveforms. So these are all signals that I captured here in Monterey over the air through Whisper system, and then I mix them together into this scene and then produce the surfaces. So this is a very real property of real signals, including the signals that you're dealing with in your radio astronomy measurements. Okay. And then it's very general. If you look at the patterns of those cycle frequencies alpha for all kinds of different signals, you'll see different patterns. And so this is what leads to the idea that you can use the spectral correlation function as a kind of a fingerprint, and you can tell what kind of signal is present from that fingerprint. So these are cartoons here. These aren't measurements in this particular slide, but it gives you the idea that there's a lot of richness to the feature that you can extract from these signals. However, and this is the bane of my existence, is expensive. It's computationally expensive. And one of the reasons is when we want to achieve that tolerance to co-channel interference and noise, we have to average for a long time. So we have these long blocks of data that we want to process. And another reason is that leads to a very fine resolution in cycle frequency. So when we try to cover the entire plane, the F alpha plane, we end up with millions and millions of point estimates that cover the plane, sufficient to not miss any features. So we have just a difficult estimation problem, and we try, there's a lot of ways to try to reduce the complexity of that, but that's just the fact. That's why it's so expensive. You have to have long blocks, and you have this resolution problem. Okay, so those were the cartoons that I wanted to show just to orient us quickly, into CSP. There's not a lot of math in those. Here's a little bit of math just to sort of fix the idea of spectral correlation in case somebody, on this call really wants to see that. So starting with equation 3, you can see that's just a sliding Fourier transform of some data X. We're sliding it along, passing a window with width capital T along some data, and we're looking at the Fourier transform at frequency F in equation 3. Then we take two of those at two different frequencies, F plus alpha over 2 and F minus alpha over 2 in equation 2. We multiply those together. And then in equation 1, we do an idealized correlation measurement using those two spectral components, X of T plus of F plus alpha over 2 and F minus alpha over 2. So that's what we really mean mathematically by spectral correlation. It's this limiting form of this correlation. And there's a bunch of names for them. On the equation 4, that we have to modify this for the conjugate. You reverse, the F minus alpha over 2 when you remove a conjugate. And all of that's on the blog too, if you want to see where that comes from. So that's what it really is. But it's very sensitive to power, as you can see. So if the signal goes up and down, then that correlation is going to go up and down. And what we want to do is process the spectral correlation function so that we can tell what the significant parts are in the plane, independent of having to know things like the power or even the noise floor. So one strategy to do that is to just normalize the spectral correlation function, which is a correlation by the geometric mean of the variances of the involved variables. Okay, so that's just a correlation coefficient, which I'm sure everyone's familiar with. And so when we do that, then it's called the coherence function, and there are many related coherence functions like this. This is the way we do it in CSP. And now this function, which is still a surface over the F alpha plane, can be easily thresholded. So that's how we're going to find blindly all the cycle frequencies in the GBO data using the spectral coherence. This whole theory of the second order stuff, the spectral correlation function and the cyclic autocorrelation, it's really just a part of a much larger, more general theory of higher order statistics of man-made signals. And so we don't need to get into all that, but here's a one slide summary of that. And if you're interested, there's a lot of information on the blog. And this is really my doctoral work, and my specialty is the higher order stuff. And all of the stationary stuff that we're familiar with, like the Wiener relationship that says the power spectrum is the Fourier transform of the autocorrelation function, all of the stationary signal cumulant polyspectra things that you can read about, all of the cyclostationary stuff, it all is really one theory. And so this is my attempt at the graphical representation of that theory. Just want to let you know that this is all embedded in a much larger theory. So let's look at some examples. So what I've done is captured some data and also simulated some data. And I just computed the non-conjugate and conjugate spectral correlation functions for all these, just so that we can see the variety and maybe get a little bit more familiar with what these things mean. So for a sinusoid, we just have the PSD in the upper part. So the sine wave comes through as a rectangle because I'm using a frequency smoothing method of spectrum estimation there, and the kernel of that method is a rectangle. So impulses become rectangles. And then you also have the single feature in the bottom, which is at the doubled frequency of that sine wave. So it's like the simplest cyclostationary signal. Here's a QPSK signal, which just has one feature at the symbol rate. And you can see the PSD at alpha equals 0 in the back, typical bandwidth efficient COM signal. A lot of these kind of signals in the GBO data. The pulse shaping filter of the signal matters. So if you have a kind of a bad pulse, like a rectangle, or any duration limited, time limited pulse, you're going to get a bunch of features, a bunch of cycle frequencies, and when you don't, you only get a few. So here's another pattern for staggered QPSK, very common signal, also seen in your data. Some signals have sine wave components, like some forms of frequency shift keying. And so you'll see these big spikes here and there, but also a continuous part to the spectral correlation function. And so it goes. So I'm going to get to the measured ones, and we'll stop there for a minute. Stop here at the direct sequence. This is also a signal that's in your data. Direct sequence spread spectrum BPSK, probably the most famous example of that is GPS, but also direct sequence spread spectrum features in things like CDMA. And so here we see a really big difference in the spectral correlation function compared to a lot of the signals I just showed. There are a lot of features. There's a lot of cycle frequencies. Alpha is still a discrete parameter, but there are about as many cycle frequencies as equal to the processing gain of that signal. And we'll revisit this when we get to the GBO data, because the GBO data that you gave me happens to contain the GPS band. Okay. DSS QPSK is a little different. There's no conjugate part of it. And DSSS SQPSK, another commonly used signal, is kind of a hybrid of those two previous signals. So here's a captured CDMA. It has several weak features that aren't shown on this plot, and a feature at its chip rate, 1.2288 megahertz. Here is a form of CDMA called EVDO, which is kind of a gang together bunch of CDMA signals that are transporting data rather than voice, and it has richer features, right? So we can easily tell when we come across CDMA EVDO by this particular pattern. WCDMA is the wideband version of CDMA. It has this very strong feature at its chip rate, which is 3.84 megahertz, and some other smaller ones in the kilohertz range. GSM, on its way out in the world, but still around, has a lot of cycle frequencies because it is a TDMA type signal. You know, it has slots that users can jump in and out of, and that framing or slotting causes a lot of features. This is a kind of thing that's seen a lot in the GBO data as well. LTE, not on its way out, is a cyclostationary signal as well. Relatively weak features, except for some below 10 kilohertz. And so you just have this huge forest of cycle frequencies that can serve as a fingerprint, but are difficult to estimate when the signal is weak. You can see they're on a grid here. Okay, so that's a whirlwind tour of CSP and how it might relate to modulation recognition. Let's talk a little bit more in detail about what modulation recognition is. Okay, so it's the problem of assigning one or more modulation type labels to a data record. We might want to assign more than one if there's more than one signal present, as there is often in the data records you've given me. And we might want to assign more than one just because we might want to assign a generic type and a system type. So we may want to say, oh, this is QPSK and it comes from CDMA. And so this is all DSP. This is all digital signal processing. So I have a sample rate FS and I have a data record with T samples in it. So that's kind of my starting point. And in the wide world, it's often assumed that that T sample data record contains one signal. It's in white Gaussian noise, centered right at 0 and all that. But we don't do that here. To orient you a little bit more, this modulation recognition problem is applicable to a lot of different situations. Cognitive radio is probably the most famous one, but also things like surveillance and interference characterization, or as a prelude to signal separation. So if you have a signal you're trying to receive and another signal is right on top of it, you may want to remove that interfering signal. And there are ways to do that, including the fresh filtering I mentioned. But they need to know highly accurate parameters of those signals that are interfering with each other before the algorithms can be effective. So it's like a preprocessor. It can be used as a preprocessor for signal separation. And you know, I've been working on it for 20 years plus, a lot of other people too. And so like, why haven't we solved it all? It's just very hard because of the many dimensions of the problem. Even people that are working on closely related problems still have differences in their problem set that are barriers to sharing solutions. So it's a very multidimensional problem. So my solution to this is to, you know, no surprise, use cyclostationarity as a sort of feature set. And I embed that into a decision theory sort of framework and come up with some classifiers. Then I build a system around those core mathematical entities. And it looks like this. So this is what I'm going to apply to the GBO data towards the end of the talk. I come in with some complex envelope data. It's exactly what I have from Ryan. And I try to find the bands of interest using a non-CSP technique. So in that case, I want to find all of the energetic non-noise parts of the spectrum. And then I'm going to process those separately. And how do I process those? Each one of them I pass through an exhaustive spectral correlation analyzer. So I find the surface. I find the spectral correlation surface as a function of F and alpha. Then I compute the spectral coherence for that surface. Then I apply a threshold. Out of that, I get a list. So once I get to the cycle frequency grouping part here, the hard part, I have a list of numbers, or really a list of like 4 tuples. And then this is all list processing. So you have to combine hard-won knowledge of all of the different patterns that I showed you with list processing type algorithms, and then you can come up with sublists, one for each signal ideally. Then you take those sublists of cycle frequencies, you compute some high resolution spectral correlation functions, and you can compare those to a catalog, a second order catalog with spectral correlation functions. And in many cases, like the direct sequence spread spectrum signals, that's sufficient. And you've done your characterization by getting the parameters, and you've done your recognition by saying this is DSSS BPSK. But in some cases, the pattern is ambiguous. There are many signals that map to a particular second order pattern. And so then we'd follow this line down to the higher order stuff, which we didn't talk about very much, but we would do some higher order statistics, cyclostationary style. And that helps us remove the ambiguity. So then we can tell the difference between, for instance, QPSK and 16 QAM, if that means anything to you. So all of this stuff is fully available, and I ran it on the GBO data. Before we get to that, which is coming up quickly, let me just give you an idea of what the kind of power that this technique can bring. So I'm doing some Monte Carlo simulations here. I'm generating signals over and over again and passing them through the MSSA and recording the results. So I'm looking at 22 different PSK and QAM signals. So BPSK, QPSK, 8 QAM, 16 QAM, 64 QAM, all the QAMs that you can think of, right? And they have an SNR of about 10 dB in band. And then I'm going to look at a couple different block lengths measured in symbols. So 5,000 symbols versus 20,000 symbols. I'm going to use second and fourth order cumulants in my cumulant matching. And then there's a certain number of trials. Now the catalog is much larger than this number of input because there's just a restriction here on the total number of signals, which is already big, almost too big to show you the result. So we'll see that in a second. But just to make it perfectly clear, this is the kind of thing I'm talking about. If you've seen a constellation diagram, here's a bunch of constellation diagrams of the signals that I'm passing through my system to do these Monte Carlos. BPSK only has 2 points in the constellation, but 1024 QAM has 1024 points. And there's a lot of different variations in the world of these kinds of things. And the particular arrangement of these in phase and quadrature components in the constellation diagrams really matters for cyclostationarity. So if we pass 5,000 symbols through per block, we get this confusion matrix. I'm not going to assume everyone knows what a confusion matrix is. So what all this is telling us is on the rows, what the input signal was. On the columns, what the decision is, okay? So ideally, you would have a diagonal of all 100s here. 100 out of 100 times, you'd get the right answer. And so the confusion matrix shows you quickly and visually what's confused for what. So many of these signals do have 100 or 99, very good performance. But once you get into this subset down here of 64 QAM, 32 QAM, things like that, you start to see some ambiguities or some confusions. And so that's kind of good news. If you don't have an ideal diagonal here, then you want sort of the dispersion away from the diagonal to be low. You don't want a signal to be confused uniformly for all the other signals. And so we see that here. Like here's an example: 64 QAM is routinely recognized as 256 or itself, right? So that's a good confusion to have. But if we bump up our block length, if we have the luxury of processing more data, then you can make that performance much, much better. There's still a few confusions. 32 QAM for 128 QAM, 64 QAM for 256 QAM is still there. And those are natural because when you look at the fundamental probability density functions and cyclic cumulants for those signals, they really are quite close. So even the machine learners have troubles with those particular pairs. Okay, so the Whisper system, it's just a hardware version of the MSSA. Don't need to talk about that too much. Okay, now let's get into your data, unless there's some kind of questions or comments. Okay. All right, so the data I have from the GBT is this channelized data. I think it's just data that Ryan had available. It's not tailor-made for CSP or ModRec, but it's pretty cool still, so we'll look at it. So we have 256 IQ channels. Each one of those channels has a bandwidth of about 800 kilohertz. And so together they span 200 megahertz. And the center frequency of that 200 megahertz is about 1.58 gigahertz. So that's what they were staring at. It's broken up into these time domain blocks. So we have channels and blocks. And the block length is about a second or 1.3 seconds. And the channelization that leads to these 256 channels over the 200 megahertz has significant roll-offs on the edges of the band. So any signals that happen to be lying, on a channel boundary get distorted. So let's just look at some PSDs. There's a polarization X and polarization Y for each one. I didn't pay too much attention to exactly what that means, but I'm carrying them around here for your benefit. So this happens to be channel 68. The reason why there's multiple traces on each of these is because I'm overlaying the PSD estimates for each block. So this is one of the channels, it happens to be channel 68, centered at something like 1625 megahertz, and it's all of the blocks. So there's significant time variation going on in this particular channel, right? We can see the signals coming up, going down. Sometimes they're there, sometimes they're not. Messy. Then you get a lot of things that look like this, where like on the polarization X, nice and flat for most of the time across the blocks. There's a couple signals. Some of them are quite stable. Some of them come and go. Other things like this, which are just, I admit I don't understand this. And then there's a significant number of these 256 channels that are empty. The little signal in the very center of each of these is some sort of a local oscillator bleed through. It's not, I don't think it's a part of the external world. So we can ignore that. And then you have signals that look like this signal between 1603 and 1604. It's pretty clear that that signal stretches well beyond the edge of the channel. And so we're only capturing part of it and we're distorting it. Same for 132 and 133. Those are like really halves of a single signal that's spanning two channels. We get a lot of things that look like this. Plenty of narrowband, quite narrowband signals mixed in with wideband signals. So I'll just start going a little bit faster. Okay, so that's fine. Anybody can estimate PSDs, but that orients us a little bit about what the data is that I looked at coming from the GBT. But if I'm going to tell you some parameter estimates and signal types and things like that, I'd like to validate my understanding of the data in your eyes. So let's do that with the GPS signal. It's centered at about 1575 megahertz, which is within the 200 megahertz band. We know a lot about it already. It's a direct sequence spread spectrum BPSK signal. It's got a chip rate of exactly 1.023 megahertz and a processing gain of 1023. That's just the ratio of the chip rate to the underlying data rate. I stitched the channels back together. I identified which channels corresponded to the 1575 band, stitched them together to make it like a 2-channel data record. So that means I now presumably have the GPS signal, but it's got some significant mid-band distortion still because of the 2 channel edges that I had to stitch together. Then I process that with MSSA. So here's what the MSSA tells me. All right, so I've got this signal. It's centered at about 1575, like we mentioned, and it's got this big notch in it, and that's just because of the roll-off of each of the channels that I stuck together. Whisper sees this band here, says, okay, I'm going to process this band, which is pretty much the whole thing, right? There's only a few hertz on either side that we don't care about. And it gives me this spectral correlation function. It's way too messy to show the surface for this kind of signal because there's literally thousands of cycle frequencies here for this kind of signal. So what I do is I just show the maximum over spectral frequency for each cycle frequency in the estimate. So it's like an edge-on view of the surface. And so we see a prominent peak here. Hopefully you can see my mouse at about 1 megahertz. It's hard to tell with our eyes exactly what that is. And then a whole bunch of cycle frequencies down below that. And then in the conjugate, we see a big prominent peak right about mid-band, twice mid-band, and then offset from that peak by about 1 megahertz. And then a whole bunch of stuff in between. And if you just look at what the MSSA is telling you, it's telling me in block 1, I have a direct sequence spread spectrum signal with processing gain of 1023 and this particular rate at this carrier, this SNR. So I don't want you to be impressed that I can detect GPS, but this validates everything Ryan told me about the data and validates how I've extracted the data from my own MSSA purposes. So when I tell you numbers in the following results for the other parts of the data set, we have some confidence that those numbers are accurate. So here's some sequence of results. So remember, what we're trying to do here is blindly determine the types of interference that we're seeing in the data, estimate their parameters, and so maybe we can point a finger. So here we have 3 SQPSK signals, 1, 2, 3. Their rates are 11.7 kilohertz, and it also tells me the carrier frequencies, which are obtained from the conjugate parts of the spectral correlation function here. So we didn't know anything about this particular data set, but we can immediately say, okay, we have 3 SQPSK signals. We can go ask somebody, hey, what system makes SQPSK signals with 11.7 kilohertz? And that'll help us understand where this signal is coming from. And so we have a lot of signals like this at 151.2 kilohertz. And you can see there's a signal here, obviously in the PSD, and another one here. They have these prominent features way out here at 151 kilohertz and some other weaker features. So that's evidence that these are probably TDMA type signals, that there's some slotting or framing in the MAC, the medium access control layer of this waveform. A lot of narrowband signals. I was surprised how many narrowband signals there are. So these are digital QAM signals with 6 kilohertz rate and an SQPSK signal with 10 kilohertz. So a second kind of SQPSK signal. We see several MRE PSK signals with rates exactly 33.6 kilohertz here, and a digital QAM signal. This signal obviously has some kind of features, but was the MSSA did not. I'm hearing myself. Okay, I'll keep talking. Hopefully it'll be muted. Okay, good. And here's an interesting one. Let's see, up at 1542 point something. It's a narrow band direct sequence spectrum BPSK signal with chip rate 16.5 kilohertz and a processing gain of exactly 25. So we can tell the carrier as well from down here. This peak is right at the double carrier of that signal, and so that's a signal that we could try to point a finger about. And so it goes. Now this is a sort of a new kind of signal to me. I was grateful for seeing. You can see it has lots of features, just like a direct sequence spectrum signal, a prominent feature out here, but it doesn't look like any kind of generic DSSS signal. If it was like GPS, we'd have three big features here. If it was like QPSK, this stuff would all be essentially negligible. And if it was SQPSK, there'd be two features. So it's either a TDMA style signal or a new kind of direct sequence spectrum signal. And we can also tell the difference between PSK and QAM and CPM. CPM is a constant modulus signal. So this signal is a constant modulus signal with rate 25 kilohertz. I think now I'm switching the title to other interesting GBO SCFs. So these are like difficult for the MSSA. It doesn't know about these patterns. So here's one where there's a lot of weak features, but no strong one. So it's similar to direct sequence spectrum. And then there's a relatively strong double carrier out here. So another DSSS TDMA type hybrid maybe. Another very strange one. I'd love to know what made this signal. It's possible that this is just a chunk of a much broader signal that stretches across some other channels that aren't being processed here, because we get an AM-like behavior. There's nothing up here except for the PSD and the non-conjugate, and then we have this single double carrier type feature, which is very AM-like, but AM is typically not a broadband signal. Okay, so that's, I would say, maybe 5% of the data that I generated using the GBO data set. It's just too voluminous to show it all. But hopefully it gives you an idea that this kind of processing can do blind recognition and characterization of signals that are in the bands that you're interested in. And then finally, I wanted to just bring up this idea, which is, so what if we wanted to actually remove some of that to see what's underneath it? Maybe sometimes a signal is actually masking something that we want to see underneath. And we can't use linear time invariant filtering. We can't notch it out, right? If we do that, we're going to notch out whatever's underneath it too. And presumably they have the same support in time. So we can't gate them out. We can't just say, well, let's just take this 2 milliseconds here and this 2 milliseconds here, because they're contemporaneous, right? So what do you do? If you have an array, you can try to steer a null towards each terrestrial interferer that's causing you problems in that band. But let's assume we don't have an array. We just have a single sensor. Can we use CSP to attenuate these man-made signals, revealing the natural signal underneath? And I think it's possible, but it's going to require some research and development. And so this is the idea of frequency shift filtering, which you can look up, in the literature. It's a class of linear filters, but they're periodically time varying, so they're not time invariant. And out of that mathematical idea comes a structure that we call a fresh filter. It's a frequency shift filter. So we take our incoming data and put it into all these branches in this diagram, and each branch is a frequency shifter followed by a linear time invariant filter or an adaptive filter. Think of them as finite impulse response filters. Okay, so low complexity type filters. So frequency shift, filter, frequency shift, filter, and you can do the conjugate stuff too. So this is for the conjugate. And so no surprise, the frequency shifts that you pick for this to work well are cycle frequencies. They're cycle frequencies of the signal that might be in R, as well as the interferers that are in R, and their sums and differences and linear combinations. So you pick some set of those, and you make this filter, and you try to get only your signal of interest out, or equivalently, you cancel out the interfere. So I have some code, that I use for fresh filtering. It's not nearly as mature as the MSSA stuff, but this is a kind of example just to really fix the idea. I created a signal of interest, BPSK signal, and that's the black line, okay? And I created two interferers, also BPSK signals, and those are the two blue lines, the dark blue and the cyan. And added them together and added noise. And so what I can observe is the red line, okay, is represented by the red line. And what I want to get out of the processing is back to the black line, right? I want to get just the desired signal and cancel out the other ones. And you can see if I just try to notch them out, try to suppress them with linear time invariant filter, I would just push down the black line too. So I can't do that. But if I program a fresh filter with cycle frequencies taken from these different signals, which are discoverable by the MSSA, I can improve the SNR of my output by something like 10 or 11 dB in this case. So the signal is not distorted significantly at all, but the effects of the in-band part of the interferers are removed. And why can we do this? It has to do with spectral correlation. So hopefully you can see my mouse. So like for this cyan BPSK signal, some spectral components over here are correlated with spectral components here. So if I can use a spectral component over here, which is not in band with my signal, to cancel the correlated component over here, I've reduced the interference inside the bandwidth of my signal. So it's that kind of idea. You use the correlation of each signal against it in the case of the interferers. And this particular example is not an adaptive filter. I solved the ideal theoretical equations for the minimum mean squared error filter using the cycle frequencies that I picked, which were the cycle frequencies related to the signals, and the PSD of the signal of interest. I didn't actually solve those equations by knowing the desired signal. So there's a lot you can do. You can start off like that, and then you can adapt. You can every once in a while refresh those equations, solve them again with new data. I don't know, but it's an interesting idea to try to uncover a natural signal from a co-channel man-made signal. This is just the errors, so you can see the red again is what we can view in our receiver, and the black is what we want, and the green is the output of the fresh filter. So, okay, conclusions. Turns out that most man-made modulated signals exhibit cyclostationarity. That just means that the parameters, the probabilistic parameters like PDFs, moments, and cumulants, are periodic functions of time, not time invariant, as in stationary signals. The patterns of those periodicities depend on how the signal is modulated, its type, and the values of the periodicities, that is, the actual period lengths themselves, reflect things like chip rate, symbol rate, the actual parameters. And we can use all that information to construct blind automatic MODREC algorithms to determine the type and parameters of signals in arbitrary data sets. We applied that to the GBO supplied data and validated it against the DSSS BPSK from GPS, and then found a whole bunch of signals in that data, lots of cyclostationary signals. And we learned something new because there's some new patterns there. So I think it's promising to be able to use this kind of technology to characterize RFI in radio astronomy, and I think there's a research opportunity for using it to separate signals. Okay, so that's all I prepared.
All right, thank you, Chad. That was really awesome. I have several questions, but I'm going to open it up to the audience first, just to see if there's anyone else who would like to ask anything. I'm going to ask that people use the raise hand function in Zoom, and then I can call on people. That way we're just not talking over each other. Yeah, Matt, go ahead.
Yeah, thank you, Chad. You can point me to the blog if you have some information on this there, but I'm curious what kind of processing hardware is Whisper using, and I guess how fast is it able to get through all of these computationally heavy algorithms, characterizations?
Right. Yeah. No, I don't talk about Whisper too much on the blog. It's more the the open theoretical stuff and examples. But my best Whisper, which is ongoing work with the NRL, is a 72 core machine, HP DL380, and I use all of those cores when I process incoming data, say at 50 megahertz or 100 megahertz wide, and I still can't keep up in real time, even for simple scenarios. So I am a couple of orders of magnitude away from real time for most scenarios, even using massive parallelization. So I was hoping that, in the context of radio astronomy, there would be a lot of offline analysis that could be done, because the real time is hard. We can gang together some of these HPC whispers to solve a single problem, because they're parallelized both by using cores and by using multiple workstations with cores. But it's a problem.
I'm going to ask a follow-up question because Matt touched upon something I was going to ask anyway. So just to provide some background for you, but I think you're kind of familiar with what we're trying to do, but also for the people on the call. The data that I supplied Chad with is just output from one of our Pulsar backends, but it's the actual voltage data before we do any additional processing and averaging, and then finally just writing the final data products that we're interested in to the disk. So that's why it's not really designed for CSP. But what we've been trying to do with some of the archival data that we have is not for the science perspective necessarily to classify what each kind of signal is and trying to recover its particular properties. We just want to know, is it human-made or is it astronomical? Because at that point, what we've actually been thinking about doing is just notching it out. And you do throw away some good data, but the hope is that you'll throw away a lot less good data if you're able to process things in real time and work with much more finely time sampled data, potentially recover some current frequencies that we just, the way we currently do things, we end up averaging for seconds and we toss out the good data with the bad if there's short time scale variation in there. And to just simplify downstream kind of processing, because what everyone ends up doing in some form or another with offline data is to go through and flag samples and frequencies that have been impacted by RFI, and usually just exclude them from analysis. So if we simplify the problem like that and not worry so much about the classification for online processing, what kind of prospects do you think there are for doing real time, and over what kind of bandwidths?
So it boiled the problem down to man-made versus non-man-made subbands. Well, I guess if you really had a great idea of the spectral shapes of all the different man-mades that you might want to flag, you wouldn't need any CSP, right? You could just do good high quality spectrum estimation and do template matching, something like that, to find some band. If you wanted to really make sure, like, is this a modulated signal? Does it have some kind of structure underneath it? Then you're going to have to do something like the SSCA. You're going to have to do some sort of blind processing to look at the internals, the internal structure of the probability structure of that signal. So I don't know. I'm not too bullish on it. being able to simplify the problem into man-made versus non-man-made, because what does man-made mean? One idea is it's cyclostationary. Another one is I have this huge catalog of spectra, and I know no natural signal is going to look like this. So that's a little risky, it seems to me. I guess that's what you're doing now, is what I heard you saying.
Yeah, I mean, we're looking at a few different techniques, and CS is one of the ones that I hope is like more robust in terms of not necessarily falsely flagging
Right.
an astronomical signal
Right.
compared
Yeah.
to a man-made signal. Yeah.
I guess I would have to be educated a little bit more on if it indeed was possible for a astronomical signal to have internal structure that similar to a man-made radio signal.
Mhm.
I know there's a lot of things that are, rotating and causing periodicities of all sorts in your work, but my sense is that's obvious, right? I mean, it's an actual periodicity, not a second order periodicity. So maybe the overlap between man-made spectra and natural is not very big. I don't know.
Mhm. Okay, I see several people with their hands up. So Evan first, then Greg, then Stephen.
Yeah, I was just I've read a bunch of pages on your blog,
Thank you.
and I might just be blind, but do you have resources for simulating those signals that you talked about? You had the big list of like all the constellation diagrams and stuff.
Right.
I'll just
No. So first, the CSP blog doesn't give a lot of code in general. I think I have one code snippet on there that generates a BPSK signal in MATLAB. Generally, the simulation of signals like in that constellation diagram slide that you're talking about is quite easy in MATLAB, and I believe in Python too. So it's like a couple of lines in MATLAB if you are willing to pay for MATLAB and then also pay for the toolbox, the comms toolbox. So those are easily made. If you wanted to send me an email, I can show you how. But generally, I don't put a lot of code on the blog. It's really a self-help blog. I'm trying to make it a self-help blog.
Yeah.
Sorry.
No, that's yeah.
Yeah.
All right, Greg, go ahead.
Yeah, thank you. So first of all, well, thank you, Chad, for the talk. That was really good, and I was reading your blog. So I've been reading it for a while. But Evan, what I know is that you can use NWRA for generating your own modulation signals, and NWRA can export binary files over which you can do some simulations of computing the spectral coherence function, correlation function. So Chad, I was just wondering, when you were showing all those signals that you were processing from the GBT data, the spectral correlation function seemed to show that even if you had different signal in the PSD, those signals, individual signals, will still trigger the same cyclic frequencies. And I was wondering if that was something that you would expect. That's the first question. It's more practical question. Second, you have pure zeros between the discrete cyclic frequencies. Right. I suppose you're thresholding in a certain way. And some cyclic frequencies seem to have a correlation that is pretty small. What do you lose in the fresh filter if you forget about some cyclic frequencies?
That second question is a really good question. What frequency shifts to use in a fresh filter is kind of an open question. There's no really great work or formula that says, here's exactly what to do. There is, if you know the scenario, then there's an optimum thing to do. There's an optimum set of shifts, but that's usually pretty big. Mm-hmm. Yeah, it's a large number of branches. So I would say that to find the right subset of frequency shifts in a fresh filter that gives you adequate performance, but is not too complex, is like an empirical question, unfortunately. Okay. Mm-hmm. Yeah. And then the first question was about if we have multiple signals of the same type in a data record, right? And what happens? Do we expect the same cycle frequencies? Is that? Yeah, we will. It can be easy or hard to then enumerate those signals based on that information. For instance, if the signals are simple like BPSK, they'll all give the same symbol rate, you know, in the non-conjugate plane. And so you're like, okay, I have one cycle frequency. How many signals do I have? I don't know. But if you didn't look at the conjugate, each one of them produces a little set of cycle frequencies at its own doubled carrier. And so Whisper MSSA can then count how many signals are present. If it's a different kind of signal like QPSK, then you have to do something else. You have to do a band of interest analysis. So I glossed over it, but the very beginning of the system, the MSSA, I try to do spectral segmentation. So that's on the blog. So spectral segmentation means breaking up the input into, there's a band here that I want to analyze, a band here, right? If you do it that way, you automatically have that enumeration coming out of it, even if they have exactly the same parameters. So there's a lot of ways to tell how many signals are present, even if they have the same cycle frequencies.
Yeah. Okay, interesting. Thank you.
Yeah.
All right, I think we have time for one more question. So Steve, go ahead.
Sure. So first thing I just wanted to say, the confusion matrix looks pretty impressive compared with some of the other deep learning research I've read on ModRec. But my question was more like, you've found some signals that your tool didn't identify. So I was curious, what's your process for expanding your library of, you know, known modulation types within your system?
It's a great question. Ideally, you know, I would find some resource, you know, in the world that said this system, you know, uses this signal in this band. And I would correlate what I found with that, and I would say, okay, I'm very confident that this signal comes from this system. And then I'd have a way of labeling that. Otherwise, and this happens in other situations, not just radio astronomy, I just say, okay, this is a new type. I make sure that I can recognize it, and I give it a pet name. And then if I see it again, I recognize it again, but I can't connect it to the world. So to really answer your question, I'd have to have an external labeling, right? I'd have to be able to definitively label it.
Right.
I can do all of the algorithm work without the label, but I can't actually say this is the signal until I get that label.
So your system, two instances of the same type of modulated signal that is unknown, you would be able to connect those somehow, but not connect that back to a system that produces that signal.
That's right.
Is that true? Okay, yeah, that's great.
Without that other information, right?
Yeah, no, I'm just more curious about, you know, like seeing instances of an unknown signal and just being able to sort those into a bin so that when we do figure it out, we can say that this is what all of these are.
Right, right. That is a capability
like
that's
okay,
something
cool.
that we can do already. Yeah.
All right, so I think we'll wrap it up there. We're a little bit over the hour anyway, but I want to thank you, Chad, again for giving us a really great talk. And yeah, if people have further questions or want more information, check out the blog. And
yeah,
be in
and
touch.
you can email me. You can get the email from Ryan.
Yeah, if you do want Chad's contact, just shoot me an email. All right, thanks everyone.
Hey, thank you so much.
Yeah.
See you later.
Thanks.